Really excited to be here and to tell you about some of the work that we're doing in building scalable quantum technologies. Now, I realize this is a quantum computing platform, the workshop series that you run, but I hope I can get you excited about some of the work we're doing in the building blocks, right? The components that I think will allow us to get to scalable quantum computers, but not just quantum computers, other kinds of scalable quantum technologies as well. The work that I'm going to talk about is done by my students and postdocs who are listed here, so they get all the credit for the awesome science. So we take a theory-first approach to both predicting and controlling new kinds of quantum systems. When I use the word quantum systems or quantum technologies, really I'm referring to everything ranging from computing, sensing, and of course, networks. The constraints for these technologies are different. So the building blocks that would be of interest are slightly different, but I'd say that the theory pieces that go into it have a lot of commonality. So within my group, we work a lot in ab initio quantum electrodynamics. In particular, how can we describe these joint interactions, these types of strong light matter coupling interactions where you treat the matter at a high level of quantization, so you're actually able to talk about the matter degrees of freedom, whether it's the electrons, the nuclei, or you're thinking about the spin degrees of freedom, at the same time as talking about the electromagnetic field. We've also done a fair bit of work in correlated electronic structure methods. And this is exciting because some of these allow us to predict better quantum systems, but also many of these problems are the ones that people are talking about as being the first problem that quantum computers will have a big impact on, right? When you ask people, well, what's going to be something that you'd be able to run on a near-term large-ish quantum computer, the answer frequently comes back as some problem in chemistry, some problem in material science, some problem in optimization, right? And all of that goes through the route of new electronic structure methods. And both of these have, of course, a lot of synergy with the second half of what my group does, which is in open quantum systems methods. We've done a fair bit of work in actually taking some of these open quantum systems methods and mapping them onto a quantum computing framework, so actually mapping them onto small quantum devices. So let me just spend a second telling you about why open quantum systems, right? When we think about a quantum system, we have the system and we have the bath. And typically, what you would say about the bath is that the bath is uncorrelated, the bath has no memory, there's a one-way flow of information from the system to the bath. Now, obviously, that would be very nice if it was just one-way flow. Well, maybe not very nice, but that would be too simple. As it happens, there is a backflow of information in many of these systems, and that backflow of information is good in a few different ways. A, it allows you to use the bath as a resource itself, and B, it allows you to think about how these types of interactions can be used to describe even larger correlated systems. Okay, and the second one is not so obvious, but I'll try and convince you that actually open systems methods are actually quite general and overcome some of the challenges that we find in other kinds of electronic structure methods. So all of this, of course, has nice synergy with algorithms, right? We think about algorithms in my group, not just from the standpoint of quantum computing, but we think about these algorithms actually in the context of very large scale classical computing as well. So the kinds of supercomputers where we've run some of these calculations, the Summit supercomputer, for example, it's been in the news a fair bit, but also upcoming architectures. Pardon me, I have a bit of a cold here. So with these types of algorithms that we're developing, we think about how we can incorporate GPUs and also how we can do hybrid quantum classical computing. And I think there are some advantages and disadvantages of doing that, okay? So all of this to say that we do a lot of theory and computation in my group. If you want to read about some of this, we've written an extensive ChemRev, I believe it's about 100 pages, and has a gazillion references for how one can actually think about correlated quantum matter and quantum computing. So when I tell people that we have this challenge of predicting, right, that really is why we are not able to scale arbitrarily, to the kinds of devices we want, people ask, well, there are methods, right? So what's the issue? So let me just describe the issue at the were in this one slide. So on the left of the slide, you'll see things that you recognize from your favorite chemistry course. These are ones where we're talking about a finite system. Okay. The good thing about a finite system is that you can directly map it, okay, particularly onto quantum devices. And this is exactly what people do when they talk about the couple cluster ansatz and how you can actually run it on some of these near-term devices. But the types of observables you get out are things like the orbital density, the potential energy surface. These are things where you can do very, very accurate calculations, but they're small, okay? On the other side of the slide, you'll see things you recognize from condensed matter, particularly analyses that reflect how do you think about a phase diagram, how do you think about phase transitions, how do you think about the band structure. And what's essential in all of these types of calculations, these types of theories, is that you have the ability to talk about an extended system, something that has periodicity, that actually gets very heavily leveraged and actually talking about the band structure, for example. But that is a very different genre of theory methods from the ones that we're talking about here on the left. And then there's stuff in the middle. This is quite exciting, but also the most challenging. For example, large molecular qubits. We're talking about transitions that involve optically addressable spin qubits. I think some of these are actually quite hard to describe with these methods on the left because these don't scale to the system size that we're interested in. But the ones on the right, where you're invoking periodicity, also don't apply to these systems in the middle. So a lot of what we do is actually method development, right? We think about how we can actually solve these problems, right? I would not be telling you that there's a big problem in the field and not telling you something about a possible solution towards it. So a lot of what we do is actually method development, right? And we have started to actually think about these multi-qubit studies, bringing together things from quantum chemistry, quantum information, as well as how we can maybe include even some intersection with ML. Okay, so let me just tell you, I like to describe things with pictures because I think that resonates with people more. I'll keep the number of slides that have gory equations to a bare minimum. Okay, so when we think about a single qubit space, now just imagine it's some optically addressable spin qubit that lives in material. Fine, no problem. I could describe this. I could describe both the optoelectronic behavior. I could describe the spin physics. I could talk about the intersystem crossing. But that's just a single qubit space. That's clearly not the only thing I'm interested in, right? What I'm really interested in is a slightly more complicated scenario where I have a single qubit space, another single qubit space. I define this nice multi-qubit space. I have some controls. And now, in this, I have also some interaction with the nucleus bit. So whether it's acting as a source of decoherence, whether it's acting as a bath that we can use, there are different opportunities there, like I alluded to. But now we have a fairly complicated problem, right? So at its bare minimum, we have the qubits, the bath, and the control. Of course, in all of these, you also need to think about how am I going to track the fact that I have entanglement, what's the right measure. I'll get to entanglement measures in the later part of my talk. So with this, we also think that there is a nice intersection in terms of designing these controls with work in and methods in ML. And physics inspired ML, so not blind ML. But how do you actually couple these? You could think about coupling them directly via the lattice. You could think about coupling them, say, via some optical mode of a cavity. You could think about coupling these via an external magnon mode. The number of choices is just absolutely enormous. And with each of those, the kinds of constraints that you put then on your single qubit space are actually different. So we're thinking about how you could go about this. With one of my postdocs, John Philbin, we wrote about this in PRX last year, so you're welcome to take a look at it. And of course, in terms of methods, I don't need to tell folks in this audience, but maybe I'll just allude to it briefly that developing new methods that treat photons, nuclei, electrons, everything at the same level of quantization is actually quite hard. So it requires developing a fair bit of new approaches. So now let me tell you, and this is where I'm going to dive into some detail of how we developed specific ab initio approaches, both to talk about decoherence, to talk about controlled schemes, and talk about open systems. Okay? The first is where we're talking about these spin qubits, and we're interested in, of course, using them either in the context of a memory for a network, or even in the context of a QRAM for a quantum computing architecture. And there are proposals out there for how one could use such spin qubits, whether they're in diamond, in silicon carbide, pick your favorite material. From a slightly more abstract theorist standpoint, of course, we just are interested in the types of interactions that are possible. So what are those, right? So I have my qubit, my defect, I have the bath, and I have some interaction term. And these interaction terms, right, there's a leading order a zero field splitting. I'm denoting the electron spin here with this red arrow, and then the nucleus spins with these blue or purple, depending on how it's showing up on your screen. So, we of course have this dipole coupling between nuclei. We have a Zeeman term that corresponds to electron, to the nuclei, and of course we have a hyperfine term that we're interested in. And this is where you realize that actually you could, you don't just have one electron spin interacting with one nucleus spin, right? As soon as you start to have something that isn't isotopically pure, or you have a bunch of nucleus spins, you'll actually have these clusters that you're interested in. And you could go back to your favorite stat mech textbook and say, well, how does one treat such clusters? Turns out that there is a way rigorously, particularly in the context of a set of density matrices that you could write for these, a way to treat it that is pretty likely to converge. And it's called the cluster correlation expansion, CCE. Okay, so let's look at the picture version of it, which is on the left. It's the same exact thing on the right, but that's the math version. So I'll stick to the picture version in the interest of keeping everyone's attention. So the simplest I can write out is a CCE1, where I have one nucleus spin interacting with one electron spin at a time, right? But then I can create little clusters of these. So I have two of them interacting with one, right? And then I could think of these. What I don't want to do is actually have every pairwise interaction that I'm going to treat explicitly. Again, going back to your favorite StatMech course, you'd immediately realize that the best I'd be able to do in that scenario is nearest neighbor, next nearest neighbor. Those explicit treatments where you're treating every interaction individually is not going to scale whatsoever. So this is an exactly equivalent approach, okay? But you very cleverly create little clusters that then interact with the spin of interest. And you can then think about propagating, and you can think about actually looking at explicit time dynamics of such a system, right? So I have this, I turn on the interaction, I have all of those interactions that I pointed out a couple of slides ago, and now I can actually look at the time evolution. And why do I want to do the time evolution? Well, because I'm looking for decoherence, right? I'm looking for a scenario where there's a decoherence event that occurs because of this interaction with this bath. But not only that, in this method that has CCE, we also have various kinds of non-Markovian effects. We have various kinds of spin echoes, and we can include things like external magnetic fields. This is actually work that was done by one of my first students, Chris Ciccarino. He is now a prize postdoc at Stanford University. So what Chris was able to show is that this method actually works not only for the simple scenario where you have one electron spin interacting with the nucleus spin bath, because that would still be that single qubit space. He actually started working on this multi-qubit space and thought about how you could actually leverage a generalized CCE approach. So now instead of creating clusters where it's just all the blue and interacting with a single red, you could actually create a cluster with each of these individually. You could create more complicated clusters, and you could actually start to talk about both the population and the coherence evolution. So both the diagonal and the off-diagonal terms of this full density matrix that you're able to track can give you essentially a sense of, am I going to be T1 or T2 limited, and what's really going to be the best thing for me to optimize associated with these clusters. So taking that a step further, we're now linking this with measurements of various kinds of qubit systems. We're thinking about actually also how to connect this with quantum embedding methods. And connections with quantum embedding methods is actually quite exciting because, you could imagine a scenario where you're treating this at this set of spin interactions and you're embedding it essentially in another way that you're treating the electron correlation, say using the reduced density matrix method. So the idea of embedding is that you have a rigorous way of connecting these various quantum degrees of freedom at different levels of theory without introducing either discontinuities or without introducing other artifacts into your calculation. So, we've been interested in this topic for some time, and that's one vignette, one example of how we've treated it. It's certainly not the only one. In fact, we've gotten very excited about how one could make these general quantum interfaces. And when I talk about interfaces here, I'm not talking about a literal interface between a material and another material, a material molecule. That's what people usually think of when they think of interface. I'm talking about a general interface, right? Like I would describe the way that I connect to my HDMI here as an interface. It's a general interface. I can move it around, right? I can move it from my laptop to your laptop, presumably, though it does not always. It should work. So when we think about what the quantum version of that is, right? We want to connect our spin qubit to our favorite quantum platform that might be at a very different scale. And the easiest to see here is when we're trying to connect it to, say, superconducting qubits. Now, this is back to that very specific example I gave of a QRAM. Doesn't have to be. There are other reasons why you'd want to do such quantum interfaces. And when you start thinking about this now, you realize the choices are, again, enormous. You could think of something that is directly dipole mediated. You could think about something that's phonon mediated. And think of something that's magnon mediated. And for each of these, the types of constraints and how you think about this actually is quite different. So, we've been thinking about how you could use optical transitions as an example, how you could actually leverage that. And of course, there's nice work that some of you, including one of the folks who invited me to give this talk, has been doing in this area. So I won't dwell on this too much, just to say that, they've been pioneering demonstrations, and our little contribution to it has been that, we could also include selective optomechanical control. So optomechanics is nice. Lots of people are working on various kinds of optomechanical cavities. I think it's a very promising approach. I'm sure you'll have other speakers to talk about it. I want to talk for a few minutes about actually a different genre of doing this, which is using a magnon. Okay, so magnon, right? So spin excitations, and of course, we immediately, when we talk about a magnon, think about whether it's a ferromagnetic material. In this case, for our purposes, it could be either. We're not limited. And what we're interested in is actually a single magnon mode that can allow us to, say, connect one spin qubit to another without requiring proximity, without needing some external cavity. I guess the magnon cavity here becomes its own cavity, so we're not putting in an additional optical or optomechanical cavity here. So when we look at the magnon modes, and now my model system here will be a sphere of YIG. It doesn't have to be YIG. It could be some other ferromagnetic material. It's just that this material is well behaved enough that we can describe it. It has a bunch of modes. And if I look at the spectral density, I might originally be a little bit intimidated and say, ooh, so many modes, so many options to couple to. But let's pick a simple mode, right? Let's pick this dipolar Kittel mode. This is omega over omega k as 1. And let's see if we can describe the coupling first of a single spin qubit to it, and then go from describing that to then two of these that are coupled via that single magnon mode. And I point you to, pioneering work that's happened in the past few years, particularly by folks on the superconducting qubit side for a single shot, single magnon detection. This is now possible. We don't have to talk about, a set of magnons all being excited at once. We can talk about using a single magnon mode. So we do that. And in fact, we can do this within the Wigner-Weisskopf approximation. We can talk about the coherence dynamics. So we can talk about at different distances, right? So if I move it very close, it turns out that magnons are very forgiving. So you could be on the order of 80, 100 nanometers away from the edge of your magnon cavity, and this should work. And in fact, the mode that we pick out is this now nice dipolar Kittel mode. It's sitting at maybe around 16 gigahertz. Okay, so now our interest was, of course, in coupling two of these with each other via the mode. So now we're showing the coupling here. The coupling here is in kilohertz. The distance here is in nanometers. I'm contrasting direct coupling, basically trying to establish that these two emitters are not talking to each other directly, that they are in fact talking to each other via this magnon, okay? And you can see that also in the population dynamics here. So what this led us to, really think about is that you could use magnons as essentially, instead of optomechanics or direct optical control, you can think of magnon-mediated gates. You can think about, all kinds of magnon-mediated interactions that could be leveraged. And we're doing a fair bit of work in this direction going forward. So as we were doing this, right, and we were talking about these very simple concepts, we started to notice that there were a lot of papers that people are writing about these molecular qubits. And he said, well, how does one think about getting two molecules that are, say, you have perfect molecular qubits to talk with each other? And how does one do that, say, using a cavity mode? Is it going to be a magnon again? Is it going to be optical, optomechanical? And more importantly, how do I track entanglement in such a system, right? So to me, it wasn't obvious that some of the ways that we, describe entanglement for solid-state systems could be, copy paste onto these molecular systems. So we were interested in how one describes it, and a very simple, thought experiment that we were trying to do here is that if I have two molecules in two cavities, I come in with entangled light, I imprint that on these two molecules. Can I actually talk about a good entanglement measure for these molecules, right? So it doesn't have to be in two cavities. They could be spatially separated within the same cavity. Turns out that people working in cold chemistry, cold molecules, have done really amazing stuff that makes this possible. But from a theory standpoint, we said, well, you could use the direct electronic modes of the molecules. Doesn't have to be. You could also think about using the vibrational modes. And here, talking about the Gaussian entanglement between, say, the incoming entangled pairs and how it's transferred to the vibrational modes actually is quite exciting, because now we have choices. We could either do something that is discrete variable, and this would refer to then the encoding of the vibrational modes of each molecule, or we could do something that's continuous variable with the coordinates, both position, momentum of each molecule. And whether we do discrete or continuous variable, the types of protocols that we could then leverage this for would actually be quite different. This is work that's being done by two of my postdocs, Scott Smart and Spira Circus. Now, these slides are courtesy of Spira. So, well, we then start thinking about, this rabbit hole of various quantum tomography methods to reconstruct the density matrix that now represents this slightly more complex quantum states, right? So turns out that, like everything, there are choices and various measures for us to characterize such entanglement. The simplest is negativity, where we think about the extent to which the Paris-Hradecki criteria is violated, and that's written as so. We can think about entanglement of formation. I think this is a little more intuitive, where you think about, what does it take to get that same maximally entangled state? How many of these, or how much of those do you need to represent the state that you've made? Or the relative entropy of entanglement, which is more of a distance-based measure, and some folks on the CS side tend to like this, which is the distance between the entangled state from the closest separable state that you can find. So what we're now thinking about is how these measures can be generalized and used in the context of cold molecule approaches, how you think about this in the context of molecular qubits. So now I want to spend a few minutes talking about, back to that open systems work, because I think this nicely relates to both quantum computing as well as to scaling quantum architectures. And we need to take a little bit of a detour here to understand everything that I'm going to talk about. And the first is this concept of course, Markovian and non-Markovian dynamics, right? So when we think about a system where there is a quantum system at bath, and the bath is uncorrelated, bath is boring, there's a one-way transfer of information, the system then can be described in this regime called the Markovian regime. And there are many ways, master equations in particular, that you could use to describe Markovian dynamics. This is actually quite well established. This could be Redfield, this could be Lindblad. Lindblad is the one that people are most familiar with, particularly coming from a quantum optics standpoint. And this is typically derived under the Born-Markov approximation, the closed propagation, and the interaction with the back, right? So this has actually been applied ad nauseum in quantum optics, but it gives us a framework for how one thinks about Markovian dynamics. Now, something I convinced you of, hopefully, is that in open system dynamics, you don't just have the simple picture where there's a one-way transfer of information. You could have backflow of information, and that itself is referred to as a non-Markovian regime. Now, what is truly non-Markovian, in fact, defining it formally and mathematically, is an active field of study itself. So I won't go into that rabbit hole, but I'll say for our purposes, we can say any backflow of energy or information from the environment to the system makes it non-Markovian. Okay. And now, again, we invoke a master equation here. In this case, the Nakajima-Swanzig equation is something that is quite frequently invoked. But unlike the Lindblad case, where all one needs to do is some dynamics, this actually has some challenges for practical implementation. And the biggest one being that you are not guaranteed the positivity of the density matrix in such situations. If you lose the complete positivity of the density matrix, of course, you end up with something that is unphysical. And we don't want to do that. So there is an approach that was developed by a former postdoc of mine, Dr. Prineha Narang. She is now a junior faculty member at Washington University in St. Louis. And what Kade was able to accomplish is this method called the ensemble of Lindbladian trajectories. And this overcomes this problem of a complete positivity of the density matrix by taking an ensemble of different Lindbladian trajectories through this state space and this few hundred trajectories. And this actually directly simulates the kind of long time non-Markovian dynamics that you would get from the Nakajima-Swanzig equation. And we found this actually to be quite interesting, because not only does it allow you to look at slightly more complicated systems, but also because this method itself can be mapped onto a quantum computer, right? And now this is a little counterintuitive. You'd say, well, you're telling me that some non-Markovian dynamics is being mapped onto a real quantum device. How are you doing that? So with some mathematical jujitsu, with combination of dilation, decomposition, as well as taking the CLT method and mapping it, you're actually able to show that you can run these as quantum algorithm analogs of what you're able to do on classical devices. And turns out that some of these give some very interesting results. Our first benchmark was a system that, again, has been studied, overstudied even, but it's the model system of the James Cummings Hamiltonian, where you look at it in the strong coupling regime, on and off resonance, and the Markovian approximation here in green says, okay, I start out and then I lose things through the bath, nothing happens. Well, we know that's not true, right? So there are other methods, and we benchmarked them, and I won't talk about all of these acronyms, but I just want to point out ELT, which is the method that Kade developed, as well as exact dynamics, a system where we can do exact dynamics, which is why we picked it as our model system. Actually, the two methods directly overlay with each other. So this is not a fit. These are two approaches that are perfectly agreeing. The exact dynamics of this and the ELT method, which is the red dots, okay? And you see this little bump here. This is their first revival. This actually means that there's like actual backflow of information, and it is appreciable if you just look at the amplitude relative to where we started out, okay? So this has been run on IBM's devices. In fact, we've written a whole series of papers beyond this, both by Dr. Hedmarsden as well as Dr. Anthony Shingen, and working together with the group of David Mazziotti. So I encourage you to look at some of those references, and if there are questions, please feel free to ask me or Kade. So not only can we apply it to abstract problems, we actually also applied it to this FMO complex, and I thought this was exciting because this was bringing a problem in chemistry together with a problem in quantum algorithms and quantum computing, where we could actually see that this open systems algorithm that we had put together can capture the dynamical population evolution of the FMO complex. And FMO is everyone's favorite fruit fly in the thinking about light harvesting complexes. but it is actually a complex system, 7 sites. We reduced it to a 3-site model. And we talk about its interactions with the bath, and we actually do this on a quantum device. So taking that, even further, this work that was done by a combination of Stefan Krasnov and today, when they were both in my group, is thinking about how we can actually learn non-Markovian dynamics, right? So I've been telling you, well, the non-Markovian is very complicated. You might say, well, why don't you just do some learning on it, right? So it turns out that doing learning or doing explicit time dynamics, the two ends of the extremes, are both kind of inefficient, but for different reasons. For one scenario, you're throwing away more physics than you need to. The other scenario, you're doing a lot of gory details that are not always necessary. Now, the other reason one might actually want to do learning on such non-Markovian dynamics is because, guess what? This is exactly what you need in order to design controls for quantum hardware, right? When we're thinking about optimal control, and we're thinking about how you could, go back to that very simple picture I had of the 2 different single qubit spaces, coupled external control, right? There are many wrong ways of designing a control. It turns out there are very few ways of getting it right. And if you could do some learning on non-Markovian dynamics, it could be pretty awesome. So we've written about this. It's a paper on the archive. Hopefully someday it will actually appear in press. But we've, introduced how you could use the study method for talking about open systems dynamics. And I encourage you to take a look at it. So now, maybe in the last couple of minutes that I have, just want to talk about some of the emerging approaches. And this is work. There are a series of papers that appeared from us in ACS Photonics over the past few months. This is work done by one of my other postdocs, Dr. Davis Welleque, where we've been thinking about, how you could use and introduce nonlinearity into some of these calculations, right? Nonlinearity, of course, being very important, and how you could use that to also talk about various kinds of symmetry breaking. So the first scenario we looked at was this gallium arsenide quantum well. It's a very, very simple system where we can actually, it's a centrosymmetric system, right? So in a centrosymmetric system, you should not get various nonlinear processes to go, especially you should not see a chi2 there. What we were able to show is that via strong coupling, via strong light matter coupling in particular, you could induce a symmetry breaking, and that symmetry breaking itself would actually allow you to make the system go nonlinear. Not only would it allow you to make the system go nonlinear, in fact, mechanistically, we have a way of thinking about it, and using that same length gauge Hamiltonian to describe the photon matter interaction. It's a dipolar self energy that you essentially end up adding to the harmonic binding potential, right? Because it's the simple quantum well. And this, together with the bilinear term, will break the symmetry. And this actually gives you the ability to not only introduce, but also control nonlinearity in such systems. I want to point out that being able to control nonlinearity and turn it on and off in a very, controllable manner for quantum devices is actually in itself quite interesting, and lots of people are thinking about it. So we can also do that with a molecular system. It turns out everything you can do for a solid state system, if you can show it for a molecular system, then you could completely claim generality. And here we're looking at not only second or third harmonic, but also very high harmonic generation. In fact, building on this, and I don't have a slide on this work, but I'll use words to describe it. We've also been thinking about how you could get some of these very, very high harmonic processes to go in patterned graphene and use that itself as a light source. So maybe not so interesting for a quantum computing audience, but we've been thinking about how you can use that itself as an attosecond source. We have a paper on that that's currently under review. So I'm trying to establish here that there is a nice link, intersection between the kind of work that's happening in devices and in predicting various kinds of devices interactions, kind of work that's happening in quantum information, and also the types of algorithms that we're developing that can run directly on quantum devices, and they themselves would allow us to design. This is like a nice feedback cycle, right? This is the circle of life. You take some algorithms, they tell you about some complicated system that you couldn't actually easily simulate on a classical supercomputer, it allows you then to design better materials, and the whole cycle keeps going. So we're quite excited about it. So with that, I want to leave some time for questions. I want to thank you for being here and accommodating my schedule. And I want to thank my group again, and happy to field any questions, comments from those of you here. And if you're interested, I am looking for people in my group, and postdocs in my group do really well. So if you're interested, please write me, and happy to chat. Okay. And let me know if there are questions. I can in the chat or raised hands.
Hello. Can I ask a question?
Yeah, please go ahead.
Hi. I am Kai Tao from Stony Brook University. I am a final year computer science PhD candidate, and I'm looking for jobs now. So
okay.
My question for you is that, do you welcome computer science background PhDs for doing a postdoc? And what do you expect from computer science background people?
Absolutely. So I've actually had people with a CS background and PhD work with me, and it's been very, very fruitful in the past. I think that there are, depending on what you've worked on in the past, if you have some interest in thinking about the complexity of some of these algorithms, that's something that we're actively looking to hire in. If you're interested in evaluating or benchmarking various algorithms, it depends on whether you come from a TCS and an algorithm background, or if you're thinking about it more from NLP. But yeah, all of these are welcome. We've in my group thought about how you could design various protocols for not just computers, but also for networks. So if you're interested in thinking about quantum networks, that could also be another direction to go in. So yes, I hope I hear from you soon.
Okay, cool. When I start looking for jobs, I will definitely email you.
Sounds good.
Okay. Thank you.
Yeah.
And I think there is a question in the chat box from Daniel. I have one question concerning feedback control in quantum systems and knowing about the measurement problems in foundational quantum theory.
Okay. Could you be a little more specific? I guess, what are the things that we are looking at I'm assuming this is in the context of the study method that you're asking this question. We're interested in how you could design controls that are optimal, but there are bounds people have shown on how optimal the optimal control could be, right? Turns out that most real methods are actually a long ways from where that bound is, but I think that this is an area where we could do a fair bit with a combination of the physics of Nakashima-Zwanzig together with the types of RNNs that we can bring to the table. I think in terms of measurement problems, perhaps you're asking, are there various metrology techniques we could leverage? And I'm not necessarily, working in that field of, testing the various quantum bounds, but there are others who are working on that. Yeah. I don't know if I'm answering your question, Danielle.
Yeah, I actually have one question for the slide 32. So I think you show the using like recurrent neural nets to do this control of the pulse signal. So is this I'm curious, do you think I think this is recurrent neural nets, but how do you do the training? So do you collect a large data set on a real device? And also, do you think other methods also work, like reinforcement learning or the zero order optimization, like the Bayesian optimizations? Mm-hmm.
Oh my gosh, yes. So actually, all of those approaches people are trying. Let me just tell you a little bit about why we went this route and what we had in mind. Okay, so we essentially have seen other work that people were talking about all the ways you could do different kinds of neural nets, and we said, well, but we've been developing all these high level physics method. So can we actually combine it? And turns out that, the training sets that you need, we had them anyways because we were doing the explicit time dynamics, right? So kind of cheated a little bit on that. But characterizing actually the properties of, the environment is not just for spin qubits, is very interesting for people working in superconducting qubits. And there we don't have necessarily as much training that we could do. But turns out, right, that if you look at current non-Markovian tomography techniques, they're either limited to discrete superoperators, or they're blindly applying various ML methods, and they're not really providing physical insights. So what we've done here is this learning architecture where we have both the physical constraints and we have the properties of this completely positive trace preserving map in a differential form. We also have an ML, this RNN approach. Now you could do better than RNN, no problem. I think that's something that we could look at. But we actually have this continuous dynamics explicitly encoded in the steady method. This steady method is it's like it's Julia code. I mean, this is like very approachable. If you are working in any area of ML, you'd be very comfortable looking at this and then seeing how other ML algorithms can intersect with it. But our key insight was to keep both the physics and the ML and maintain that positivity of the trace preserving map. So that's the key insight.
Yeah. Okay. Yeah, gotcha. Thank you. I think there is another question from the chat.
Oh, how do you address phonon-induced inhomogeneous dephasing in your model? Excellent question. So in the work that I showed, we have separately the spin physics, and we have separately the phonon-induced processes. And this is where I use this word quantum embedding, and we are going to combine from a couple of different theory methods. And that's the sleight of hand that I did. So it's not the same method to treat the dephasing that is from interaction with spins and the dephasing that comes from interaction with the lattice. We have them from different levels of theory, and we kind of put that in. Yeah. And of course, you always have some in homogeneous Brande, you always have some dephasing that you attribute to the phonons. The question is whether that's the dominant source or not. And you can look at that by looking at how it behaves as a function of temperature, for example, and that gives you some insight.
Hi, can I ask a question?
Yes, go ahead.
Hi, my name is Victor from Johns Hopkins University. So I've been working on quantum control and open quantum system for a while. And I'm wondering, for the work that you mentioned, you're modeling the Markovian dynamics in quantum systems. So one of your model is really consistent with the exact Markovian dynamics. What do you mean by
exact non-Markovian dynamics?
Exact non-Markovian. What do you mean by exact here?
Yeah. So this is a system that you could do, exact dynamics on using Nakasima-Swanzig, because it's a simple James-Covey model. And that's where we were able to benchmark it relative to our ELT method. Yeah, that's, yeah. And that was just to show that what we were, and these are all, the ELT here is run on a quantum device. So we wanted to make sure what we were running on it is actually robust. Yeah.
So are you running the ELT model on the IBM superconducting?
Yeah, exactly. Yeah, we've run it on some of their premium devices, and that's been, a good experience. There's a series of papers we've written beyond this initial results. I don't have slides on it, but I could send them to you if you're interested. Or you could find them if you find, Kade and me. Yeah.
Thank you.